When you're working math problems, do you ever feel like you're just going around in circles? Well, prepare to feel like that on Category 3 for integration by part. In this case, we'll consider integrands that are the product of an exponential function and a trigonometric function. So both factors in this product are transcendental functions. That means, for example, if we differentiate an exponential function, every single higher order derivative will also be an exponential function. If we look at a trigonometric function, like sine, for example, and we continue taking derivatives, well, we're always going to be alternating between a sine function and a cosine function. So we're going to attempt to reproduce the original pattern of the integrand by applying integration by parts twice. Then we're really just going to outsmart the integral by solving for it algebraically. Let's give this a try on example 4. We have the integral of e to the 2x times cosine of x dx. Now, it doesn't matter which part you choose for u and for dv, but we are going to do 2 rounds of integration by parts. So just remember, the nature of the function that you choose for u on the first round has to be the same nature that you choose for u on the second round. So in this case, I'm going to start out and let u be the exponential part. U equals e to the 2x. Then we would recognize that du is 2e to the 2x dx. Now we're also going to choose dv to be the leftovers in the integral. In this case, we have cosine of x dx. We're going to integrate both sides. On the left side, we get v, and on the right side, we end up with sine of x. Now notice, when I'm working this particular category of problem, I am going to make sure and write the original integral over here on the left side. That's an important step because we're going to see this integral reproduced on the next round. But for now, we're going to apply our integration by parts formula. We have u times v, that's u e to the 2x, times v sine of x, minus the integral of v, which is sine of x, times du, which is 2e to the 2x dx. One of the goals of integration by parts is to make this second integral easier to evaluate than the original integral. But in this case, we have the same category of integrand. That is, we have an exponential function times a trig function. So we are going to do another round of integration by parts for this integral. So looking just at this integral, and let's take one step to move that 2 out of the way, just to clean it up a little bit. We have e to the 2x times sine of x minus 2 times the integral. I'm going to switch the order of the terms, e to the 2x times sine of x dx. So for this second round of integration by parts, again, I'm going to let u be the exponential part. Okay, remember, you can choose either the exponential or the trig part for u, but whatever you choose on the first round, be consistent and choose that same type of function for your second round. Also, you can recognize that this was your first u substitution. This is your first v, so you can call this one u sub 2, v sub 2 if you wish. I'm just going to indicate the difference using color here. So I'm not going to use subscripted variables. du in this case is 2e to the 2x dx. So this part is going to be u. The leftovers here then will designate to be dv. So dv is sine of x dx. The integral of dv is v, and the integral of sine of x is negative cosine of x. Be careful with the signs there, the signs. Integral of sine is negative cosine. So continuing with our problem here, I'm going to copy down this first term, e to the 2x sine of x, and then I'm going to expand this integral using the integration by parts formula. But do remember, it is multiplied by a negative 2. So since this integral is going to turn into two terms, that is u times v minus the integral of v du, I will need a set of brackets here so that I can correctly distribute that -2. So applying integration by parts, we have u, which is e to the 2x, times v, which is negative cosine of x, and I'm just going to move that negative there in front of the exponential. We have u times v minus the integral of v. Now notice again, v is negative, and I'm subtracting this integral, so that double negative is going to make a positive. So we have v times du, and du is 2e to the 2x dx. Now before we proceed to the next step, let's simplify just a little bit. I'm going to distribute this -2 to both terms inside brackets, and while I'm at it, I'm going to bring this constant coefficient also in front of that integral. So let's see what we end up with. We have e to the 2x sine of x plus 2e to the 2x cosine of x. So I'm distributing a -2 here and factoring out a 2. That's going to give me a coefficient of -4. And then I'm going to switch the exponential and the cosine factor just to make it readable. Now look at the new integral that integration by parts has yielded. We have the integral of e to the 2x cosine of x dx. That matches our original integral exactly. So we have reproduced the original integral. Now don't worry, we're not going to go through another round of integration by parts, but we are going to recognize the original integral over here on the left side has been reproduced on the right side. So I'm going to manipulate this equation and solve for the integral of e to the 2x cosine of x dx. So we're going to treat this integral just like an ordinary algebraic equation. We're subtracting this term on the right side, so I'm going to add it to both sides of this equation in order to collect all of those integrals together on the left. So when I add this integral to both sides, it cancels on the right. Again, this is just solving an algebraic equation. Our unknown just happens to be an integral. Now simplifying over here on the left, we have one integral of e to the 2x cosine of x dx plus 4 times that same integral. So when we add those together and combine like terms, we have 5 times the integral of e to the 2x cosine of x dx. And what's left over here is e to the 2x sine of x plus 2e to the 2x cosine of x. Now we're almost there. Don't forget to keep an eye on the original problem. Our goal is to execute this integral. We want to know what's the integral of e to the 2x cosine of x. At this time, we have 5 times that integral. So I'm going to solve for the integral by dividing both sides by 5, or you can think of it as multiplying each term through by 1/5. So I'm simply going through and dividing all of those terms by 5. Again, you can think of it as multiplying by 1/5. That's going to cancel this coefficient on the left. So we end up with, on the left side, the integral of e to the 2x cosine of x dx equals 1/5 e to the 2x sine of x plus 2/5 e to the 2x cosine of x. I'm just missing one thing. Do you know what it is? This is an indefinite integral, so we always need an arbitrary constant of integration there on the right side. So we didn't actually execute that integral, we sort of outsmarted it, right? We went through 2 rounds of integration by parts that yielded the original integral, and then we were able to algebraically solve for that original integral to find the antiderivative. So this will happen when you have this case, an exponential function times a trigonometric function. Recall that you can choose u to either be the exponential part or the trigonometric part. Just make sure you're consistent on your 2 rounds of IBP. What nature of function you choose for u on the first round, choose that same nature of u on the second round. So what I mean by that, at this step, we would not want to choose u to be the cosine function and dv to be the exponential function. We might get into a little bit of trouble there. So anyway, I think that's kind of a cool problem, but remember that strategy when you come into that particular category.